Okay, let's start. So in the last class, we started to look at how to implement the switch. Right. So we started with a simple NMOS switch like this. So this is V in. To turn the switch on, you apply VDD. And if you recollect, the on resistance for this was 1 by mu n Cox W by L into VGS minus VTH. So here the gate voltage is VDD. Source is roughly at V in. So the on resistance is a strongly nonlinear function of the input. So this acts like a good switch for values of V in close to 0 or low values of V in, and not a great switch for high values of V in. And then we saw PMOS transistor works well for V in which is close to VDD and not close to 0. So that motivated us to put these two guys in parallel to form the CMOS switch. You can remember, if this is clocked at 5 for the PMOS, it should be 5 bar complement. So this is 5 bar and 5. And this can take in input voltages in the entire range from 0 to VDD, right? Oh, sorry, yeah. NMOS is 5. That's. And we also saw that if we can, in principle, if we choose mu n Cox W by L of the NMOS to be mu p Cox W by L of the PMOS, then we expected that the on resistance was constant, independent of the input voltage like this. And let's say you want to achieve this condition also. So for switches, how did we choose the lengths for the transistors? Length is minimum. So both NMOS and PMOS have the same minimum length. So the only control you have is the width. Okay. But of course, we saw that this is impossible to realize. I mean, impossible to guarantee in practice. So in reality, the on resistance for a CMOS switch will not be constant with input. You'll definitely see some variation with the input. Okay. And this is particularly problem because this dependence is nonlinear. So if you were to apply a time varying signal, say a sinusoid, and then look at the output samples, the samples will be heavily distorted. And the reason is, if you recollect, when we had, let us say, a sinusoid of the form V naught cos omega naught t, and we had a finite on resistance for the switch, the output voltage had a transient portion that decayed to 0. In steady state, the amplitude was this guy, omega naught square r on square c square. And even the phase, if you recollect, we had minus tan inverse omega naught of c. And here the on resistance is a nonlinear function of the input. So the overall output will be heavily nonlinear. But this is not particularly a problem if you are dealing with held signals like this. I mean, even here the signal is kind of varying over time. But in one clock period, or for the period for which the switch is on, the input doesn't change. So the on resistance also remains constant in one clock cycle. Although the on resistance will vary from cycle to cycle. And here it's not a problem because if you remember, for a constant input, the response of a first order RC circuit looks like V in into 1 minus e power minus t by tau. So the error was V naught e power minus t by tau. And we are interested in the samples, so we look at the waveform at say Ts by 2. So the error was basically Ts by 2 times R on C. So if you had to choose R on C to be much smaller than Ts by 2, this term easily decays to 0, right? But here it is not the case because the nonlinearity is coming due to this 1 by square root and tan inverse, which are much more stronger nonlinearity than this. Okay, this can be easily made to go to 0, but this not. And even if you don't look at the expression, even qualitatively speaking, so let's say I consider the same thing. So let's say this is V in of t, switch, and the problem now we are facing is the on resistance here is a nonlinear function of the input, right? So let us say this is V in of t, this is V out of t, this is C, and let's say the switch is closed now. When the switch is closed, the current is, let us say, I of t. So in terms of the input voltage and the current, what is V out? It's basically the input voltage minus the current times the R on, and the R on is a nonlinear function of the input, right? And remember that the same current flows through the capacitor as well. What is the current flowing through the capacitor in terms of its voltage? Here, what is the voltage across capacitor? So it's C dV out by dt times the nonlinear function of V in, right? So basically now you see that this nonlinear portion multiplies with this guy and generates a nonlinearity, and we are only interested V out of t. We are only interested in the sample, so we put t as ts by 2, right? So this nonlinear function multiplies with the slope of the output voltage at the end of the sampling phase, and that's how the nonlinearity manifests. Now let us say the input is constant, say something 0. The switch is open for a total of ts by 2, right? If you recollect, this was the clock period. The switch is on for half the clock cycle. So we are interested in ts by 2. Huh?
You wanted the
I mean, this is the output voltage as a function of time, yeah. But we are interested in the sample here, because that's what is getting sampled. Yeah. So this is clear. Let's say we assume the input is constant, which means that over the time interval for which the switch is on, the input is constant. Say it's some V naught, and in that case, the output is going to rise exponentially like this, right? And if the output is rising exponentially like this, what can you say about the slope of the output here? Slope of the output is almost 0. As long as you choose the RC time constant to be small enough, the output voltage will settle close enough to the required input. So which means the slope of the output becomes closer and closer to 0 towards the end, right? So this guy will actually tend to 0 if you have a constant input, and that is why you see that even though this is nonlinear, this is multiplying with 0, so it won't affect us. Okay, but that won't be the case if the input is time varying. So let us say the input is varying like this, the output will also vary like this. So the slope will be non-zero at the end of the sampling phase. Okay. So bottom line, if the input is constant or held, the nonlinearity is not a problem. Only if it is time varying, it is an issue. So the CMOS, that's what, see, we can either have some kind of signal like this or a continuously varying signal. So it is okay to use CMOS switch in these cases, not for these cases. I mean, in this case, you will have not a lot of nonlinearity, that's all. Okay. So the bottom line is, if you have an NMOS switch, use it for constant signals close to 0, PMOS close to VDD. CMOS switch can support the entire range, but it is a good switch for these kind of held signals. Right, so if this is clear, let me ask you this. Let us say I take this CMOS switch. Let's say I apply a sinusoid here. I look at the output samples. Let us say the sampling rate is fixed. I do 2 experiments, wherein in the first experiment I apply a low frequency sinusoid. In the second experiment, I apply a high frequency sinusoid to the input. And I mean, if the sampling rate is Fs, what is the maximum sinusoidal frequency I can apply without Fs by 2? So this is basically high frequency close to Fs by 2. Okay, so in both these experiments, I am taking the output samples. See, and remember that because the input is continuously time varying, I will expect nonlinearity. Okay. So I take the output samples and look at its spectrum and see the strength of the harmonics. So in which of these 2 cases do you think the nonlinearity will be more? Low frequency or high frequency? Why? Sorry, more? No, I mean, there is no aliasing, right? I will assume that it's, yeah, closed fs by 2. The issue is not with aliasing. We are interested in the nonlinearity. I mean, in which case did we see that nonlinearity is not an issue? For what kind of input the nonlinearity is not an issue? For a constant input, we know that if this is the interval for which the switch is on, if the input is constant like this, we saw that it is fine. Now, one case I have a low frequency sinusoid. So it's a very low frequency signal. It will vary slowly like this, right? And in other case, it will do something like this. So for the low frequency case, you see that the input almost looks like held. Okay. For high frequency, it varies a lot. So the linearity actually will be better in this guy. And as you keep increasing the frequency of the input sinusoid, you'll also see the nonlinearity to be more pronounced. Okay. So this is simulation results demonstrating that. So again, so here I am applying a sinusoid. And remember that when we measure the spectrum using FFT, we always follow the same principle. You decide the number of points. So here I have chosen the number of points of DFT as 1024. My FS I think is 20 megahertz or 25 megahertz, I don't recollect. And I choose my input frequency. How do I choose it? It's of the form rational times Fs, and M and N are co-prime. Okay, this is how we should choose. And here I do the same thing. And I keep varying this M to change the input frequency, ensuring that it is still co-prime to N. So x-axis is the frequency where it's normalized to Fs. So this is 0 to Fs by 2. And in y-axis I am plotting the signal to noise and distortion ratio. So in this there is no noise, only distortion. Okay. And as expected, you see as you increase the input frequency, the signal to noise and distortion ratio also degrades. Okay. Right. And if you look at the expression here, yeah. So the term that is resulting in nonlinearity is this guy, omega RC, right? So how do you want this term to be? If you want to reduce the nonlinearity, what should you do to this term? You should be much smaller than 1. Then this will become close to 0, and this can be neglected in comparison to 1. So that says my on resistance must be much smaller than 1 by omega naught C, right? So now let us say you made a CMOS switch and you find that the nonlinearity is not good enough. If you want to reduce the nonlinearity, what would you do? Let's say you make a CMOS switch, you find that the nonlinearity is not good enough, you want to improve it slightly further. What would you do to improve it? From here, from whatever we have seen now. I mean, to keep the nonlinearity, to reduce the nonlinearity, this condition must be satisfied, right? The lower it is, the better it is as a linear switch. So if I were to reduce nonlinearity, what should I do?
For a given omega naught, we can change.
For a given omega naught, let us say, what should you do? I should basically reduce R on. If I reduce the on resistance, you do expect that the linearity will improve. Okay. And again, I can show some results for that. Yeah. So this is the old plot which I showed. And here the on resistance is I think 4 times smaller. And you see that the distortion performance also improves. And how much will it improve? I think you can sit and calculate. Okay. And and remember that for any MOS switch, the on resistance, how is it proportional to, how is it related to the W by L? It's inversely proportional to W by L. For any switch, we already saw that we have to choose this guy to be the minimum length. So if you have to reduce the on resistance, what should you do? I have to increase width to reduce R on, right? And the bottom line, we have to keep this guy to be much smaller than 1, right? So now let's say you're trying to sample faster and faster signals, which means omega naught is increasing. Even the required R on has to be much smaller. right? So for very high frequency signals, if you are trying to sample it, the required R1 might be really small, which means the size required will be really large.
That will increase the capacitance.
Yeah, so that's what I'm coming at. So if you increase the size of a transistor, what is the issue?
Capacitance.
So
So that
okay, let me draw here.
addition of that, like, will come in parallel of that.
No, let's look at it, right? No. So if I increase the width of this guy, what capacitance increases? Gate capacitance increases. So what? So let's say CG is increasing. What's the problem? The current where?
CGA was like,
Yeah, I mean effective capacitance at the gate is increasing, right? All capacitors are proportional to the area.
clock,
So
clock has to drive a larger capacitance.
yeah, exactly, right. See, remember that this gate we are feeding a clock signal to turn the switch on or off, and this has to be driven by some buffers, right? And that's basically some kind of inverter chain, right? You'll have, let's say, so many inverters to drive it, and the moment you increase the capacitor to make sure that the clock is also rising fast enough,
You have to increase the number of.
you'll have to not increase, you have to make the inverter stronger. See, if you have a CMOS inverter driving a load, if the load capacitor increases, you have to increase the sizes of these guys. So which means these guys will consume more power. I mean, at any point, if the load capacitance or the load capacitance increases or the load resistance decreases, the main issue is the stage driving this load will have to consume more and more power. Okay, so that is why this is not a great solution. And even in this case, you see that I am able to, at close to fs by 2, the distortion is less than 85 dB or so, right? Somewhere here. And this is not good enough in many cases, right? And we need much better linearity. So let us see what can we do for that. So I'll consider the NMOS switch again. So this is input V in. And to turn the switch on, we will apply a gate voltage VDD. So what is the gate to source voltage? What is VGS? VDD minus source voltage is approximately V in. Okay. And since VGS is proportional to VDD minus, is VDD minus V in, the on resistance is also a nonlinear function of V in. And this dependence of input voltage on the on resistance is the problem for us. If the switch were to become linear, the on resistance must be a constant, right? If you want the on resistance to be constant, what can you say about VGS? If the on resistance must be constant, what can you say about VGS? VGS must also be a constant, okay? And this is a constant, and for a switch you want the VGS to be small or large. For the switch you want the VGS to be as large as possible. So what would be the value you can choose for this? VDD. I mean, in principle, if you apply a gate to source voltage of VDD, irrespective of the input voltage, then the on resistance will be constant. Okay. So if this point is clear, let's see how we can do that. So this is the NMOS. So here the voltage is V in. If the gate voltage must be, gate to source voltage is if the VGS is VDD, what should be the gate voltage?
VDD plus VTH.
VDD plus VTH, no. V in, VDD plus V in. Okay.
Sorry.
Fine.
Sorry.
Now this has a constant VGS of VDD. So this means in principle what I am doing is I am taking a battery, the value VDD, and putting across this. In principle, if I were able to do this, this should work, right? But of course I can't keep switching, sending one battery for each switch in my circuit. So what is the best thing you can do? I mean, what is the next best thing available? You can't have a voltage source. What is the next best thing you have for a voltage source? I mean, if a capacitor is charged to some voltage, it is going to hold it, right? So instead of a battery, I mean, a battery is like an infinite capacitor, right? So again, in principle, if I take a capacitor, charge it to VDD, and connect across my switch, this will also work. So if this voltage is Vin, the capacitor top plate will be Vin plus VDD. This is true as long as I don't draw any current from the capacitor. The moment I draw current from the capacitor will lose its charge, the voltage will be disturbed. Okay. So this looks fine, but let us say you charge.
We cannot control this switch.
We'll come to that, bro. I mean, when the switch is on, I mean, remember this is the.
How to off it? How to off it?
Yeah, we'll come to that, right? When the switch is on, this is what you want. And even here, if you just charge the capacitor to VDD once, and then every time you want to turn the switch on, if you put the capacitor across the transistor, because of the parasitic capacitors at these nodes, the capacitor will lose its charge, right? So it won't be VDD all the time. So what should you do? In the point is you can't charge the capacitor once and assume that things will be fine. So what should you do? You have to repeatedly refresh the charge across the capacitor, right? And that you can do because when the switch is off, what do you want the gate voltage to be? To turn the switch off, 0 is more than enough. I'll connect it to ground. During this phase, the capacitor is not used, right? So now I can actually go and put the capacitor and charge it to VDD. This is VDD and this is ground. So when the switch is off, your gate voltage is 0, you charge the capacitor to VDD, and when it is on, you put it across the transistor. Okay. So this is the circuit in two phases. Now we'll have to combine it and draw a single circuit. So again, when the switch is on, I'll assume the control signal phi is 1. Here the control signal is 0. So this is the main switch. Now when the control signal is 0, we want the gate voltage to be pulled to ground. So what should I put here? Only when phi is 0, I want this guy to be pulled to ground. So what should I put here? I mean, in principle, ideally, what should I put? We need to put a switch that basically pulls the gate voltage to ground. And what should be the control signal for that switch? When phi equal to 0, this should be active, so this should be phi bar. Okay. And similarly, when the switch is off, when phi is 0, the capacitor also needs to be charged. So I'll take the capacitor and charge it to VDD. No, the point is we want to keep a constant VGS, and that in principle you can do it by having a voltage source across the transistor. Of course, you can't put a voltage source across each thing. You don't have voltage sources, so you put a capacitor instead. I mean, a capacitor charged to a particular voltage, as long as you don't draw any current from it, will maintain the voltage. So you can use it to boost the gate voltage.
We are charging it from a source VDD.
Correct. We have supply VDD.
VDD is not a battery. It is some source.
No, that is a battery. But see, the point is there are two things to it, right? You have lot of switches in your circuit. You can't be connecting, everything to VDD like this. And second of all the voltage supplies, you see that the negative terminal will be ground. You never have a floating voltage source like this where you can access both the terminals. In our case, we actually need a floating battery where both terminals are there. But in practice, all the voltage sources will have a grounded supply. Okay. Great. So yeah, so we also have to charge the capacitor to VDD, and so I'll do it like this. It's really slow. Okay. Again, this should be clocked at 5 bar. And when the switch is on, I'll have to put the capacitor across a transistor. So what I'll do is I'll connect it using 2 more switches. Fine. And this should be clocked at what phase? 5. So this in principle will be able to keep the gate to source voltage of the transistor to be constant. So the on resistance will be completely independent of the input to a large extent, right? And this is called gate bootstrap switch. We'll come to that. Yeah, that's the next point. I don't know why it's not writing properly. It's called gate bootstrap switch. Okay. But as he mentioned just now, we started off with the goal of designing one switch, but in that process we seem to have added 5 new switches. So we'll see how to implement those 5 switches. So I'll label these guys. Let's say it's S1, S2, S4, S5. And remember, as of now, we have 3 candidates for switches: an NMOS switch, PMOS switch, or a CMOS. So we should use either of those here. We actually copy this. Let's copy the entire thing. Yeah. So let's start with say S5. If you look at S5, its goal is to connect the gate voltage to ground, right? So here we are trying to connect some voltage to a constant voltage which is ground. So what kind of switch is good? NMOS should be good enough. So S5 is now an NMOS switch. So let's say use a different color. And this should be clocked at 5 bar, right? So actually what I'll do, I'll keep this also active. Hold on. Let me have this also, we'll draw it separately. So this is now an NMOS switch, clocked at 5 bar. So next let's look at S2. So here again the job of this switch is to connect this node to ground. So what switch is good? Again an NMOS is more than enough. So again let me just copy paste it down. Let's say put it here. So this is VDD. So this guy is also replaced with an NMOS. So this should also be clocked at 5 bar. Okay. So actually let me label these nodes here for a second. Let's say this is Vx. Okay, so let me copy this once. Sorry, hold on, let me, okay, understand, hold on. See, for a transistor, the source and drains, they don't make a lot of loops, whatever. For a transistor, the source and drain terminals, they can be anything, right? See, it doesn't matter what you mark as source or drain. For an NMOS, the terminal with the lowest potential will act like a source. For a PMOS, the terminal with the higher potential will act like a source. So it doesn't matter what you mark. Drain and source are symmetrical. You can connect anything to anywhere. The role of the terminal will be determined by the potentials between these two, right? If in this case this will act like a source, but doesn't matter. I can mark anything. Great. So now let's actually look at what switch. Let's say look at S3. Okay. Yeah. So S3, if you look at it, when the switch is on, it is trying to connect Vx to Vy. Here, right? And remember, this is going to be my input voltage, Vin. So this will be connected to V in. So what will be this voltage? V in plus VDD. V in plus VDD. The capacitor is charged to VDD. Vx will be V in plus VDD, right? So when the switch is on, it is trying to connect Vx to Vy, and these guys will be at V in plus VDD, which can be around 2 VDD, right? Because V in can go close to VDD. So what kind of switch is good enough here? It's a constant. I mean, let's say it's a very high signal. What switch is good? PMOS is good for voltages which are very high. So we can try to use a PMOS here. And here the switch is clocked at 5. So for PMOS, what should be the control? 5 bar. Okay. Fine. Great. We can also see if the gate signals we'll give for the switch is good enough to turn it on or off. So let's say when the switch is on, we want phi to be 1, which means phi bar is 0. So which means the gate voltage for the PMOS will be 0, right? And when the switch is on, the gate voltage is 0, and this will be at VDD plus Vin. So that is more than enough, right? So we'll have a case like this. This is 0, this will be VDD plus Vin, the switch will turn on without any issues. And when you want to turn it off, you will apply the gate voltage to be VDD. So the gate is VDD. And when the switch is off, phi is 0. So this portion will be connected. So Vx will be at what potential? VDD. So this will be at VDD. Okay. And this potential, where is it? Yeah. So this is actually, did I do it wrong?
But the dynamics will be very different. Right?
What dynamics?
Like, this will take from Vx will take time. Like first S1 will get close, it will take time to get VDD.
Yeah, I mean S1 is, see, these two switches are active at the same time, right? In one
This
phase.
will get close and this will get open at the same time.
No, that we'll see how we are going to do that. See, the thing is, assume that the switches are not overlapping. When one closes, one opens. Okay. Okay, so this is fine. So let's.
Certain delay, right? You cannot.
There will be delay. So what's the problem? I mean, the only goal of this guy is to keep the VGS to be constant and equal to VDD, right? When the switch is off, we'll have the case like this. The capacitor will be charged to VDD. If you take some time to charge, let it charge, right? But the moment you connect it here, this is acting like a battery. This voltage increases, this will instantaneously increase. There will be no delay. Okay, this is like a battery. So the moment Vin changes, this guy will also change instantly to VDD plus that voltage. Let me actually. Yeah. So now let's look at S4. And if you look at S4, what it is trying to do, it is trying to connect this node. Let's say this is Vz, this is Vx and Vy, and this is Vin. Okay. It is trying to connect Vz to Vin or Vin to Vz. So is there some other switch in the circuit which is also trying to connect Vin to some other node? Huh? No, yeah, S4 is what we are looking at. See, S4 is trying to connect V into this guy. Is there some other switch here in the circuit which is also trying to connect V into some node? This main switch is doing the same. So I am using NMOS for that. So it also makes sense. I try to use the same NMOS for S4 also, right? Not a lot of thought put there, but that's okay. So we'll do this. But again, remember that when you want to turn the switch on, if you apply a gate voltage of VDD, that won't be enough because the switch S4 is doing this, gate is at VDD and the source is at Vin, right? And then that is not enough to turn the switch on, and Vin can be close to VDD. So this gate voltage of VDD will not be enough to turn it on. So in principle, if I have this guy to be at VDD plus Vin, that should work. And when the switch needs to be turned off, what is the gate voltage I will need to turn it off? 0 should be enough. Okay. So when phi is 1, we want this. When the control signal phi is 0, we want this. This is 0. So now look at the circuit here and see if any other node is behaving the same way. That is there some other node which is connected to VDD plus Vin when phi is 1 and is getting pulled to 0 when phi is 0. Vy, this guy, right? So for this guy the same thing is happening. When this phi is 1, this is connected here, so this will be VDD plus Vin. When the switch is, when phi is 0, this is getting pulled to ground. And you want the same behavior for this node. So what can you do? You can basically connect them. Okay. But of course, this shouldn't be a case like, where you connect a motor and a generator and expect perpetual motion. So let's quickly see, if this will work. So the issue is when the switch is getting turned on, right? So let us say the switch is on now, that is phi is 1. Okay. And remember, before the switch is on, before the phase, when the clock phi becomes 1, it is 0 initially. This is Vz, sorry. Before phi is 1, the phase was phi is 0. In that phase, the capacitor was charged to VDD and the connection was this, right? So to start with, Vx was at what potential? VDD. It was initially at VDD. So you'll say Vx is at VDD initially. And let us say Vin is VDD. Okay. Now Vx is VDD. So when phi becomes 0, this switch turns on. So at that instant, what will be Vy? No. Vx was just before the switch was turned on, just before this switch was on, Vx was at VDD. So at the instant I turn it on, what do you think this might be? Assume that it's VDD. This will not be happening like that, but let's just say it is at VDD. So Vy will also initially start at VDD, let us say. And remember that Vx will be equal to Vy, right? This when the switch is on, phi equal to 0, right? Sorry, phi equal to 1, yeah.
Before that,
see, this switch is closed. When phi is 1, phi bar is 0. This is closed. Vx is shorted to Vy. I am saying just before the switch is on, Vx was at VDD. So let's say it is also at VDD right now. Vy will also start from VDD, let us say. Is that okay? And I know that this is now at VDD now, and this guy is also at VDD. So the gate voltage is not enough to charge this node, make this guy go to VDD, but it will not reach VDD, so it will reach to some other voltage. So let us say Vz initially goes to some V hat, which is not equal to VDD. But the moment Vz increases to V hat, what will happen to Vx? It will become VDD plus V hat, right? So Vx will instantaneously become VDD plus V hat. So will Vy be. Okay. Yeah. And once this increases beyond VDD, the switch will turn on better. So which means this voltage will keep increasing, and finally it will settle to VDD. Okay. So finally this will become VDD. And both these guys will become 2 VDD. Of course, this will not happen in steps like this. It will all happen instantaneously in one shot. There will be no delay. Okay. Okay, so then we are left with only one more switch. Let's quickly look at that. Copy. So last is S1. This is VDD. So again, if you look at S1, its job is to connect this node Vx to VDD. So what switch is good? PMOS should be good enough. So let us say for S1, I try to use a PMOS. This is VDD. So here we have clocked it at 5 bar. So what should be the control for PMOS? 5 inverted. So again, let us see if the gate signals we give for the transistor is good enough to turn it on and off, right? So let us say you want to turn the switch on. To turn the switch on, this is when phi is 0. When phi is 0, to turn the switch on, what would be the gate voltage you will apply for the PMOS? To turn the switch on, what will be the gate voltage you apply? 0. So in that phase, this is the circuit. Okay. One side is at VDD, this is 0, more than enough to turn it on. Now let's look at what will happen when we try to turn it off. So this is when phi is 1. And to turn it off, what would be the voltage we apply? VDD. So let us see what happens. So this is still at VDD. Gate is also at VDD. And remember that when phi is 1, this switch is on, right? And this is also connected. So what will happen to Vx?
Start with VDD and then go to VDD.
Yeah, VDD plus Vin, right?
Okay.
Vx will be at VDD plus Vin. That will be the voltage here. Okay. So this will be VDD plus Vin, which can be as high as 2 VDD. So now do you think the MOSFET will be on or off? Again, remember, for a PMOS, the terminal with the higher potential will act like the source. So here this is at a higher potential. So this will now become the source. And the MOSFET will be on or off? Till on. This is at 2 VDD, this is at VDD. It will easily turn on. But that's not what you want. You want this to be off.
That can never happen, right? VDD is the
Yeah, we will come to that. We want this to be off. Is that clear? We want this to be off. But as of now, this gate voltage is not enough to turn it off. So what is if this is at VDD plus Vin, what should this gate voltage be to turn it off?
VDD plus VDD.
If that is also equal to VDD plus Vin, it is fine. So let's say I want this also to be VDD plus Vin. So again, let's look at the circuit. We want, when phi is 1, we want this guy to be at VDD plus Vin. When phi is 0, we want this guy to be 0. So is there some other node here which is doing the same thing? Vy is the same if you think about it. Vy is connected to 0 when phi is 0 set. And when phi is 1, we have the connection like this. So this is connected to VDD plus Vin. Okay. So what should I do then? I'll connect the gate voltage to this guy. Okay. So this is the complete circuit. Okay. And here again, one nice thing is you don't need to clock phi and phi bar, right? Everything is now clocked at phi bar. So just one clock is enough, and that will do the job. And again, this will keep the gate to source voltage to be constant, equal to VDD, irrespective of the input voltage. So the on resistance will also be constant. So expect that the switch will be very linear. Okay. And again, this is a simulation I'm showing. So here, if you recollect, these were the plots with the CMOS switch. So this is a CMOS switch. This is also the same CMOS switch with 4x higher width, or 4 times smaller on resistance. This here the Oron was 4x smaller, and the white curve is with the gate bootstrap switch, and you can clearly see that it can easily get 110 dB of linearity performance, even close to fs by 2, and it can even get better.
What is the ideal dB you require?
Sorry?
Ideal dB you require, like
I mean, in principle I want infinite dB, right? But in practice it depends on the application. Okay. See, if you are looking at very low speeds, that is, the frequency fs by 2 will be really small. In that case, see, remember that for a CMOS switch the problem was making omega naught R on C to be much smaller than 1, right? If you are dealing with really low frequencies, omega naught, you can basically size the CMOS switch to get the R on to be small and get the required linearity. It all depends on application. Okay, great. So bottom line, we have 4 candidates for switches. One is an NMOS switch, and this is a good switch for held or constant signals close to 0. So it is an ideal candidate if you want to do something like this. If you want the switch to be connected to ground, you can nicely use an NMOS. This. Similarly, for PMOS, it is a good switch for held or constant signals which is high or close to VDD. So this is an ideal situation for a PMOS. And here, if the switch is clocked at 5, I'll do 5 bar. And the CMOS switch is again a good switch for a held signal like this. It's not becoming held. And it can take the entire range from 0 to VDD. And the last is the gate bootstrap switch, which I'll show it like this. The transistor and a capacitor put like this. And this is a best choice for sampling a continuously time varying signal to get a good linearity. I mean, but of course you can also use a gate bootstrap switch in any of these 3 cases. But that's just an overkill, right? I mean, that's like taking AK-47 and killing mosquitoes, right? I mean, same thing, you can also use a CMOS switch in any of these cases. You can use a CMOS switch even if the input is close to 0. But the problem is, anyway, CMOS is comprising of NMOS and PMOS. The PMOS will not be functional for 0 input, so it's as good as using an NMOS. Okay, great. So now this is the first non-ideality with respect to the finite on resistance of the switch. This is a gate bootstrap switch. So I'm saying this is the best candidate for sampling continuously time varying inputs to ensure good linearity, right? Because all these guys, the moment the input varies, the on resistance varies, it will create non-linearity. Here you are keeping the VGS constant, so the Oron is constant, right? So this is the best candidate if you want a very linear switch. Okay. So now let's move on to one more non-ideality, and that is also related to the on resistance of the switch. So let's say this is the model for our switch. And right now this R on can be the on resistance of any of the switches we have seen. Okay. Now ideally, if the input is 0, we expect that the output samples are also 0, right? But unfortunately that is not the case because of the finite non-zero temperature, the electrons in the resistor, they have some random motion, and that random motion induces random current, and because of that, if you look at the samples, it will be some small non-zero values like this. And this is the thermal noise. Just a second, let me close and open and see. Ooh, it's really slow. Yeah. So let's see if this is better. Okay, it's not better. Let's see. Yeah. Thermal noise. Okay. And this is basically due to the random fluctuations of the electrons in the resistor. And usually to model this noise, what we do is this: we take this noisy resistor. We'll assume that the resistor is noiseless and the culprit is some other voltage source, hypothetical voltage source in series. So this is noiseless.
Why do you consider this terminus? Is it not very small?
How small is again dependent, right? I mean, small means in relative to what? So this is the point I'm making. Let's see, hold on.
Because we never considered this thermal noise anywhere, right? In analog circuit design, we never considered.
Yeah, because you are first introduced to first circuits, then you start to look at non-idealities, right? See, first you make sure that make sure that a circuit works properly, and then you start considering all things that can go wrong. And the first thing that will go wrong is this guy. So this is a noiseless, and we have a series voltage source that models a noise generated. And again, this is a random signal, so we look at statistics. Yeah, what is the mean of this? What do you think this will be?
Zero.
Yeah, the mean of this noise will be 0. Again, simply speaking, if the mean were not 0, from the noise you can get a DC. You can use it to power everything, right? That's not happening in world, so it's not 0. Second is the path spectral density. Again, this can be proven, but I'll just give the result. Yeah. Okay, this is not working. Let me switch to one notes. Yeah, okay. Yeah, as we saw here also it's a problem. Okay, mean is 0. And the path spectral density, just a second, let me switch off the Wi-Fi. Is 4 kTr. It is a white noise, and the value 4 kTr whole square per hertz. So this is the one-sided PSD. And again, K is the Boltzmann constant. What is its value? Boltzmann constant. What is the units? Huh? Joule per Kelvin, right? Remember, KT is energy.
Okay.
So K should have joules per Kelvin, and T is the temperature in Kelvin, and R is the resistor value. Okay. Great. So now this is the circuit we have. We are interested to find the noise samples across the capacitor. Again, we are interested in the mean squared value, and the path spectral density. These are the three quantities that we'll look at. So before we look at this circuit, let's actually look at a simpler circuit, which is simple RC like this without a switch. Right? Again, to model the noise, I'll assume that I have a voltage source Vn that generates noise. So this has a path spectral density 4 kTr. And let us say I'm interested in the continuous time voltage V out of t now. Okay. So what is the output path spectral density in terms of the input? The input path spectral density times the magnitude of the transfer function square. Okay. And here the transfer function you can compute, that will be 1 by 1 plus j 2 pi frc. So if you do this, this will be 4 kTr by 1 plus 4 pi square f square. So if I were to sketch it, it will look like this. This is f, this is SV out of f. It will start at 4 kTr and then drop like this, and the corner frequency is 1 by 2 pi RC. Okay. And if I were to find the mean squared value, how do I do it? I'll integrate the path spectral density, take the area. So this guy I'll integrate. So I'll let you do the integration. This will turn out to be KT by C. Okay. I mean, one result to remember is if you actually can work it out, if you integrate this guy from 0 to infinity, you'll get 1 by 4 RC. I mean, this fraction. It's a nice result to remember. So 4 KTR. Oops. Today everything is not responding. Okay. Great. Yeah. So basically 4 KTR times 1 by 4 RC gives KT by C. Again, for those of you looking at this result for the first time, it might be surprising because the noise is generated by R, but R is not coming in the mean squared, and that's simply because, say, if you reduce the value of the resistor, this drops down, but the bandwidth increases, so the overall area remains same. Okay, wait. Yeah, this is path spectral density mean square, and what do you think the mean of the output is? 0. It's a input has a 0 mean, output is 0 mean, but is it true for all cases? I mean, let's say I take let's say some signal begin which has 0 mean. I give it to any system. Can I expect that the output mean is 0 all the time? Not LTI also. I mean, this has to be a linear system. Okay. I mean, if not, see, if this is, let us say, a nonlinear system which is doing x square, right? Your input has 0 average, so let's say it is doing something like this. If I take this square, this all like this, so you will get a non-zero average. I mean, in fact, this is how people try to generate power from noise. You need some non-linearity to generate a non-zero average from a zero average. That's anyways aside. But yeah, the result you should remember is this. Okay, doesn't want you to remember. Too much dependence of software. Let me close and open again. Let's see if this is better. Okay, maybe this is better now. Yeah, the path spectral density looks like this, 4 KTR, and the mean squared value is KT by C. This is even worse. Let me switch over to that. Yeah. The result you should remember is the mean squared value for this guy is KT by C. Path spectral density is a low pass characteristic like this. So now let's look at our circuit. So in our case, we have the switch here. So this is the noise. Okay. And let's say RC. So let us say this is the clock control for the switch. And what are the sampling instants here? Falling edges. So these are the sampling instant. So let us say this is NTS, N-1 TS. And let us say now we are operating in this region. That is, the switch is closed. And we are in this time period starting from here. Okay. So when you close the switch, the capacitor already has sampled the noise in the previous clock cycle. So that is going to be here. So this already has some initial voltage, say V0 of N-1. This is, let us say, V0 of T. Right? And we are interested in the noise sample here. Okay. Now when you close the switch, you basically have two things happening. One, the initial voltage V0 of N-1. What will happen to that? The capacitor had an initial voltage. What will happen to that? No, I mean, see, this is a linear network. The capacitor has an initial voltage which can be thought of as an additional voltage source. We have two inputs. Linear network, how can you analyze? I can use superposition. So let's say I don't consider this, I consider only this guy. So what will happen to the output? I mean, basically now I have a capacitor which is charged to some voltage. What will happen to the capacitor voltage? Discharge, right? How will it will discharge? Exponentially it will discharge. So this will discharge and it will go as V naught of n minus 1. Fine. And the second thing is the second excitation Vn, that will try to charge the capacitor to some other new noise voltage. Okay. So Vn will charge. Fine. And we are interested in looking at the sample at the end of this guy. So this duration is Ts by 2. So here I'll put the time to be Ts by 2. Fine. So V naught of n minus 1. And if you recollect, for a switch, how do you choose the RC with respect to Ts by 2? Much smaller. So if this is much smaller, what can you say about this guy? 0. Okay. So this is one observation we can quickly make. That is, the noise sample at say the nth time instant has no dependency on the noise samples of the previous time instance. Okay. So in a more mathematical sense, I can write as V naught of n is completely uncorrelated to all its previous noise samples. So now we have a random signal which is uncorrelated. So how will its autocorrelation look like? It's an uncorrelated signal. How will its autocorrelation look like? Sorry? No. If I try to find the autocorrelation, let's say R V naught of m. Yeah. But how will the shape look like? It's uncorrelated. So basically, only at 0 time shift I'll have maximum, and there will be no correlation to the next samples. So everything will be 0. Is that fine? So if this is the autocorrelation, what will be the path spectral density? It's a flat. Okay, so in single-sided PSD from 0 to pi, it will be a white noise. Okay, so this is the first observation. So if this condition is satisfied, that is, the RC time constant is much smaller than your time period for which the switch is on, the effect of previous noise samples will completely discharge to 0. So you'll end up with a white noise sequence. Okay. But remember, this is, the two things you have to keep in mind. If we just have a continuous time RC like this, wherein I look at the continuous time voltage, its path spectral density was doing this, starting from 4 kTr. This is in continuous time. But what we are saying is, if I basically take samples of this noise and look at the discrete time path spectral density, that will be flat. Okay. Now I know that the mean squared value for the continuous time noise, what is that? It was Kt by C. Now I am taking samples of this noise. What do you think the samples of this noise? No, okay. I mean, the continuous time noise had a mean squared value of Kt by C. I am sampling this. After sampling, what will be the mean squared value? Will it be same, different, or higher? I mean, same, higher, lower. You are taking a signal, you are sampling it. The power is changing or not? It shouldn't change. Okay, so it will also have the same. Again, I am giving a loose explanation. That's enough for us. Even this will be Kt by C. Okay. I mean, I can show some other explanation maybe. So remember that my continuous time path spectral density was this guy, right? This is a single-sided, so I'll draw a two-sided path spectral density here. So let's say this is my f-axis, 0. The two-sided PSD looks, let's say, something like this. Okay. Now what I'm doing, I'm sampling this noise. 2 kTr, exactly, yeah. Okay. What I'm doing is I'm sampling this noise. In time domain, if I'm sampling, what will happen in the frequency domain? We'll have periodic repetitions around multiples of fs. And here, let us say this is 1 by 2 pi RC. And remember that we choose RC to be much smaller than Ts by 2. we do expect that Fs will be, so which means I can write the other way, 1 by 2 pi RC will be greater than Fs, right? So I'll have repetitions, and the first repetition say happens somewhere here. This is, let us say, Fs minus Fs. So we'll have one repetition say here. We'll have one more repetition around minus Fs. So let's say draw it like this. And in discrete time, I'm looking at a two-sided path spectral density from minus pi to plus pi, right? So this corresponds to what frequency in continuous time? Minus Fs by 2. So I'll have to look at the spectrum only in minus Fs by 2 to plus Fs by 2. So let us say that is somewhere here. Okay. So now you can see in this portion we have this guy. On top of it, this portion is getting added. This portion is getting added. Again, because of infinite repetitions, we'll find that the entire curve will actually get superimposed on this and get added. It will get added, right? I mean, here you see this portion which is here that got added here. Yeah. So this portion which is basically this that got added here. Now from multiple repetitions, everything will get added. So finally the entire curve will actually get superimposed on this and it will get added, and you will end up with a final white noise. This is in discrete time. Okay. And to find the discrete time mean squared value, we'll have to take the area under this curve. Now we already know that this entire curve has actually fallen here. So the area of this guy is same as the entire area of this guy. And the entire area of this guy was kT by c. Is that okay? And that is why these noise samples will also have mean squared value of kT by c. So the bottom line, if you are trying to sample any signal, because of the fact that the switch has a finite resistance and because of the random noise in the switch, the output samples will not only contain the input samples but will also have the effect of noise. And this noise has a wide PSD, and the mean squared value is kT by c. And please remember, this is always true. Mean squared value being kT by c is always true. When is this? How did we get this condition? Wide path spectral density. Basically here we assume that the noise samples had no correlation to the previous samples. So here we had it. If you choose RC to be much smaller than Ts by 2, then this is valid. And for a good switch, you anyways will do that. So this is true if RC is much smaller than Ts by 2. I mean, I can also show what happens if it's not followed. So let us say I have a case where RC is greater than Ts by 2. So what will happen in this curve? The bandwidth will be much smaller here, right? So maybe I can redraw. So the same thing I will do, but here I am assuming the RC bandwidth is really small. So let's say it does something like this. Okay. Again, I am sampling this noise. We'll have repetitions around multiples of Fs. So let us say Fs is somewhere here. So we'll have the first copy repeated here. One more copy repeated here. So again, this will all. Okay. So do this. This is the. So now again, let's say this is my minus Fs by 2 to plus Fs by 2. The portion that adds is very small. So the overall path spectral density will also look something like this only finally. This is no longer white. But still the fact that the entire curve getting added on to the existing portion happens. So the mean square value of this will still be kT by c, which is still the area of this guy. So mean square value is always kT by c. The shape of the path spectral density will depend whether you choose RC to be much smaller than Ts by 2 or greater than Ts by 2. For a switch, we choose it to be less than Ts by 2, and that will guarantee a white noise samples. Okay. So what will happen now is that, let's see. So you'll be sampling the signal, and in practice we have differential signals. So let us say this is sampling the positive. See. So let us say this is sampling the positive guy and this is sampling the negative guy. So we'll have two sampling networks like this. And let us say this is VO, I'll also call it VO plus and VO minus. So VO plus of n will be Vn plus of n plus some, let us say Vn1 of n. This is the noise. So this will be Vn minus of n. Remember that this is R, let's say R and Cc. Both of them will have a mean squared value of Kt by C. And finally, we will be interested in looking at the difference VO plus and VO minus. So we will have the actual signal Vn plus minus Vn minus plus. In the differential case, this will be the effective noise. And please remember that, do you think these two noise samples are correlated or uncorrelated? They are uncorrelated because the noise here is coming due to this resistor, the noise here is coming due to this resistor. They have no relation. So even Vn1 and Vn2 will be uncorrelated. Okay. So if you were to find the total noise power in the differential signal, I'll basically try to do this expected value of the noise square, and this will be simply sum of the mean squared values of the individual signals. Okay. Because we'll have the cross term, because of the fact that they are not correlated, this will be 0. So what will be the effective noise power? It's 2 Kt by C. So basically, if we have uncorrelated signals, you can directly add their powers. Okay. Because the cross term will go to 0 because of the fact that they are uncorrelated. Okay. So last thing. So, sorry? Yeah, this will be, let's say, some plus delta V and this is minus delta V. This will be correlated. See that? See? Yeah, so now you know that if you have an ADC, we have a differential, let's say, input. I'll show a differential input like this. So at the output, we both have the quantization noise and the thermal noise. Now what is the mean squared value of the quantization noise? Delta square by 12. And for a differential sampling network, this was 2 Kt by C. As of now, it is 2 Kt by C. Okay? So now you want some signal to noise ratio from your ADC, right? You'll know what is the maximum signal power you can have in your circuit. So that will give what the noise power must be. Now as a designer, it is your job to budget this noise among quantization and thermal noise, right? So you can have basically 3 possibilities where the quantization noise is much smaller than thermal noise. Thermal noise is much smaller than quantization noise, or both of them are roughly the same orders. Again, in which case we'll choose which, we'll see later, and it depends on the application strictly. So if you find that making quantization noise smaller is very easy, it doesn't cost you a lot, you go ahead and do that. Because it's easy to reduce quantization noise, you will do it. In some cases, you will find that it might be easier to reduce this guy, so you might do it. Or in some cases, you will keep both same. So again, this will depend on application. We'll see slowly in the course. Yeah, we'll stop here.